Now let's compare the acidity in acids, right? So let's look at our baseline. Our reference will be ethanoic acid. Okay, this is our reference here. Now if you extend the chain of the R group longer, like here, propanoic acid, it becomes a weaker acid. Why? We learned before. We have a few effects that judge and governs the relative acidity of the carboxylic acids. 3 of them: hyperconjugation, inductive effect, and resonance. If you happen to come across this lecture without seeing the lectures on inductive and resonance effect and hyperconjugation, please go back and watch these videos first before you continue with this lecture. I know you can't wait, but you have to, if not you get lost in time. Right? Okay. Now carboxylic acid are acidic. You don't say right, the acid is here to give resonance stabilized carboxylic salt. Basically, the resonance structure causes it to lower the energy of the system for the conjugate base, because now you're having 2 electronegative oxygen to share and split this single negative charge, so it's somewhat stabilized. Notice again the use of this kind of double hit arrow. It means resonance structure. Here, this kind of double hit arrow indicates equilibrium, reversible reaction. They are different. Let me warn you again, you must take note of this. Very vital. Do not use the wrong arrow. If not, you get arrow to your knee. Now, for both of these carbon-oxygen bond, they are somewhat similar in length, because now we're having like a averaging of the CO bond, because this oxygen takes turn to take the negative charge, so it's like, it's always jumping here and there, so you never know when it stops. So you're having like an average structure. So that's why when you draw it out, we put this resonance structure and the dotted line to symbolize that the pi bond can be on top or below. The Na plus, which is a counter ion, just sticks somewhere to the middle. Okay, but if you look at the original molecule, then of course there is a difference in the bond length, because it was CO double bond and then the other side is CO single bond, and the O there connects to a H, so it's different. Now substituents that stabilize the carboxylic anion relative to the undissociated carboxylic acid will drive the equilibrium position towards the increased dissociation and result in increased acidity. Wow, that was a long sentence, but let me just cut it short, make it simple for you. Basically, when you consider something to be acidic, it means that the conjugate base can be formed. If the conjugate base is stable, which can exist on its own, and does not have to go back, it means that the original acid is strong. Remember the previous slide, you have equilibrium reactions. Undissociated acid become the conjugate base. So it's like, some kind of seesaw balancing act. Which side owns? Which side owns? Now if we have a lot of fluorine group, electron withdrawing group, via inductive effect, they pull electrons to themselves right and away from the CO. It means that for the conjugate base, the negative charge is shared, is split, is averaged out. So you do not have a very concentrated negative charge that could potentially attract back the H plus and go back to the acid form. And that's why you have a more acidic carboxylic acid. OH, because of the electronegative oxygen, you also pull electron density a bit and average out the negative charge, and hence stabilizes the conjugate base. Now this is our reference here. I told you before, our acetic acid that just have CH3, very ordinary, very plain, like Jane, and this is our reference. So if you put in something that's electronegative, electron withdrawing, it will stabilize the conjugate base, stronger acid. Now what about electron donating and other substituents here? Now this is our benzoic acid. Okay, our reference in the middle. We try to put CH3O, the methoxy group. Lone pair here that can push electrons into the ring, alright, and it will increase electron density to the oxygen here of the conjugate base and intensify the negative charge, which means that it becomes very negative and it wants to attract something positive, which is in the form of H plus, and goes back to the acid form. That's why comparing benzoic acid against p-methoxybenzoic acid, this is a stronger acid. And conversely, when I have an electron withdrawing group, like an NO2 group, this is one of the best electron withdrawing group that you can find. Right? Via inductive again, you pull electron density from the double O. Not the bar. The charge is shared again to a wider region and hence becomes more stable, and so this acid is stronger. Now recall that if we oxidize an alkyl group that's adjacent to the benzene ring using a strong OA like permanganate, high temperature, reflux it, we get the acid, benzoic acid. Very good yield. We could also oxidize a primary alcohol or aldehyde into the corresponding carboxylic acid. Remember this? The Jones reagent. Revision, huh? Jones reagent. Chromium 6 oxide. What color? What color? Orange. Right. And hexanal, using Jones reagents, you get the hexanoic acid. We could also make the carboxylic acid by using the hydrolysis of nitrile method. Basically, now we have a C-N triple bond. Recall the slides over the past few slides. We just need to heat it in either the basic or acidic medium, and of course if you're using the basic medium, you could acidify it to get back my carboxylic acid. Just need to heat it up using some acid or alkaline medium. Just pick one and you're good. And this is one of the ways that we can make a very common drug, ibuprofen. Ask your friends who are doing chemistry major and they will tell you that after year 3 they would have made this drug in the lab. Super cool and fun. Right, I was teaching them how to do it, but nothing like Breaking Bad. Okay, now recall that the CO double bond of a carbonyl group here is able to be attacked by nucleophile. So in this case, the nucleophile is like a Cn minus. Remember, negative charge is on the carbon, not the nitrogen. It attacks, break the pi bond and the O minus, and after that, it is good. Then here, likewise, you dope it. Remember doping? Hack in life. Cn triple bond is something like a CO double bond. So nucleophile attacks it and you get an imine anion, right? N negative. So you see this analogy? Try to dope it.